Hello. Oui. Welcome back, everybody. So we are going to start this session of UPSLA on machine learning. The first talk is going to be given by Joseph Neel on Duet. And this is actually a paper that won the SECM SIGPLAN Distinguished Paper Award. Congratulations on that. And with this, please.
Thank you. Cool. It's almost too loud. Okay, so my name's Joe. I'm from the University of Vermont. I first want to say thanks to all the awesome people that worked on this. David Darais is here, also from the University of Vermont. And we had a lot of awesome students, both at UVM and at UC Berkeley, who also worked on this and did an awesome job. I want to say a special thanks to Alex Silence, who wasn't on the paper. He's a new undergrad working with us, and he built the browser-based front end that I'm going to show you at the end of the talk. So this is only kind of a machine learning talk. I'm going to be talking about data privacy as well. So Duet is a programming language for verifying that a program gives you differential privacy. Okay? This is a program that implements gradient descent in Duet. And Duet says, first of all, that this program satisfies differential privacy. And second of all, it tells you what is the privacy cost of running this program. Okay? So that's what Duet is designed to do. So I want to first talk about what differential privacy is. So show of hands, who's heard of differential privacy? Okay, so my job's a little easier. Who could explain it to their friend? One person. Okay, David should be able to. Right. So I'll talk about differential privacy kind of quickly. So the goal of any privacy-preserving kind of analysis technique is to reveal trends in data. This is a good thing. We want to be able to learn something from the data that we collect, but without revealing information about individuals in the data set, right? So we want to learn trends about the population, but not anything about individuals. And we have techniques that we've used for a long time to try to solve this problem. The primary one is de-identification, right? You take identifying information out of your data set, then you can release that data set and everything's fine because there's no names in it, right? It turns out this doesn't work at all. And starting about 15 years ago, we started to see lots of examples of this failing to work. A very famous example of this was with the Netflix prize. So Netflix released a whole bunch of movie ratings data. Their goal was to have machine learning researchers help them improve their recommendation algorithm. And what actually happened, in addition to that, is some researchers took this data and combined it with Internet Movie Database data, which did have names attached to it. And they were able to re-identify the Netflix customers. And Netflix actually canceled their follow-on contest because of this. This is a favorite example of mine, though it's less well known. This guy, Anthony Takar, he wrote a really interesting blog post about this. He took New York City taxi data, which was de-identified, and then he went to celebrity gossip photo websites and got pictures like this one of celebrities getting into cabs. And he looked at the timestamp on the photo and the location of the photo, and he was able to figure out which trip in the data set corresponded to the celebrity's trip. And I really like this one because it's so surprising, right? If I'm the person who's deciding, how am I going to de-identify this taxi data? I'm never in a million years going to think, oh, well, somebody might go find celebrity gossip photos and connect those to my data set, right? And the kind of more general lesson here is, if you de-identify a data set, it's pretty much always the case that it is possible to construct an auxiliary data set, like the celebrity gossip photos, which will allow you to re-identify the data set, okay? So the general lesson is anonymization just doesn't work. And that's the context for the kind of rise of differential privacy, right? So everybody's heard of it now. It was really a product, it came out of the fact that anonymization techniques were subject to these re-identification attacks. And so theoreticians started looking at how can we create something that will be resistant to these attacks. So differential privacy is a definition of what it means to have privacy that is designed to be resistant to these re-identification attacks. So here's what it says. Imagine you have two databases. Database number 1 doesn't have my data. Database number 2 does have my data. And otherwise, they're identical. Okay? So the only difference between these two is my data. If I'm an analyst trying to do bad stuff, trying to learn something about me, and I run some analysis on these two databases, and I get two results, differential privacy says those two results had better be pretty similar, right? So the basic idea is you shouldn't be able to look at this result and figure out just from looking at the result whether it came from running the analysis on this database or this one. And if these two results are similar, then you won't be able to figure that out. The outcome of that is the analyst can't tell from just looking at the analysis result, was I in the data set or not? And if they can't tell whether I was in the data set or not, that means they also can't infer anything about properties that I might have. Okay? Now, I said these two have to be pretty close together. So what does that mean? I'll be a little more specific. It's parameterized by what's called the privacy parameter, or epsilon. It's also called the privacy budget. If you've heard of differential privacy, this epsilon, or the privacy budget, is maybe something you've heard of in conjunction with it. It's a continuous source of consternation when people talk about differential privacy. But this epsilon basically says how close do the results have to be in order to satisfy the definition. So how do you get differential privacy? Basically, you add noise to stuff, right? And this is the other thing you've probably heard if you have heard of differential privacy, is the way that you get differential privacy is you take an analysis that might reveal something about an individual, and you add noise to the results so that the presence or absence of an individual in the original data is masked. And so the big question is, how much noise do you have to add? And the answer is, it depends on F, and that's why building something like Duet is difficult. Right? You have to analyze the analysis that you're trying to do to figure out how much noise to add. So I want to give some examples of Fs that are good and bad. So if I have a query like this, how many trips were taken in New York last year, this reveals a trend in the data over the whole population. A single individual, if you remove them from the database, it's not going to change the answer to this query very much. But if I write a query like this that says, if Joe lives in Shelburne, Vermont, which is where I live, then return whatever to 100,000, otherwise return 0. If you take me out of the database, then the answer to this query changes by 100,000, right? So we say the sensitivity of this query is very high. And what we want to do is add the smallest amount of noise possible to achieve differential privacy, but not add more than that. Because if we add more than that, then we're kind of getting inaccurate results unnecessarily. So we have this definition. We have the basic idea of let's add noise to stuff to get the definition. So theoreticians then kind of went wild and built a whole bunch of stuff on top of the definition. This is kind of a selection of results in differential privacy over the past 15 years or so. There's a whole bunch of variants of differential privacy now. I'm going to talk about some of these later because some of them are really helpful in getting more accurate results out of your analyses. And there are a whole bunch of different mechanisms. So what kind of noise do you add? Well, there's lots of different ways to add noise. The one I'm going to talk about most is the Gaussian mechanism, which adds Gaussian noise. There's also a bunch of properties of differential privacy. So if I first run one analysis that satisfies epsilon 1 differential privacy, then I run a second one that satisfies epsilon 2 differential privacy, then I can add up the epsilons, and that's the total privacy cost of running them both. So if I have an algorithm that looks like this is from a paper that describes a gradient descent algorithm with differential privacy. I basically think real hard about it, and I decide how much noise to add. Here's how much noise they're going to add. And the way that I know if it's the right amount of noise is I kind of string together a bunch of things from this table as my justification for the idea that this is the right amount of noise to add. Okay? So this is how differential privacy has been proved for algorithms in the past. The big problem that I see with this is if you're a regular programmer and you want to write an algorithm that's going to satisfy differential privacy, and you don't really know much about differential privacy, it's really easy to get this thing wrong, right? It's really easy to add the wrong amount of noise, either too little or too much. And the problem is differentially private algorithms, when you have a bug in your algorithm, when you add the wrong amount of noise, it doesn't crash, right? It's different than other kinds of bugs in that respect. So incorrect differentially private algorithms don't crash. They silently violate your privacy. So if you add the wrong amount of noise, your program still looks like it's working. But in fact, it's silently violating your privacy. And so I think this is an especially important place to apply verification techniques because we really want a static guarantee that we've added the right amount of noise here. And it's really difficult to write test cases that'll tell you the answer to that. Okay, so what do we actually do in Duet? So there's a lot of previous work on doing this kind of verification because clearly it's a good target for it. one of the things that was really lacking in previous work was it was difficult to support some of those later variants that I listed in that table. So in particular, in previous type systems that use the kind of linear typing approach that I'm going to show you here, they couldn't support epsilon delta differential privacy. And this was something we really wanted because some of the machine learning algorithms that we wanted to write really relied on epsilon delta differential privacy. We also built a set of expressive matrix types and an API for that so that you could write machine learning algorithms. And this is something that was lacking in previous work. And finally, we have the ability to mix together different privacy variants of differential privacy. So I'm going to focus on this one in the rest of the talk. But real quick, I wanted to show you this graph, which shows you the importance of using the different variants of differential privacy, right? This is the accuracy of a model trained using a differentially private stochastic gradient descent algorithm, okay? And this is the epsilon that we used when we added the noise during training. So the algorithms that achieve good accuracy farther to the left are better, right? So this golden line is the best one because it gets good accuracy with a small epsilon. That means high privacy. These are all training with the same level of privacy, right? So if I look at an epsilon of 1, this model and this model and this model are all providing the same level of privacy. And what this shows is that if you use the thing that gives you the gold line, you get much better accuracy for the same level of privacy. And this is really the motivation for being able to support these different variants of differential privacy. These, if I use this gold line, is the ZCDP variant, which I'll show you more later on. By using these variants of differential privacy, you basically get extra accuracy for free. Okay? Okay, so Duet is called Duet because it actually consists of 2 languages. So I want to show you this example again. This is what I showed you from the first slide. These 2 pieces of it, the green pieces, are written in what we call the sensitivity language. So we have one language for tracking sensitivities. Basically, you write down the function that you actually want to compute without privacy in the sensitivity language. And then the privacy language is kind of all the surrounding stuff. How do you add noise to stuff, and how do you combine things that you've added noise to? So we have an interface between the 2 with things like this. This mgauss function adds Gaussian noise to something. Okay? Now, a key thing here is that the languages look the same. So the programmer doesn't have to actually know that there are 2 languages, right? In a sense, it's really that we need 2 type systems. And I'm going to tell you why in just a minute. So first I want to talk about how do you use linear types to track the sensitivity of functions, right? And this is not something we invented. So this was introduced in 2010 by a paper that described a type system and programming language called fuzz. And the idea is basically that a function is sensitive to its inputs if by changing one of the inputs you get a certain amount of change in the output. So if I have a x plus x, if I change x by 1, then the output changes by 2. So we say it's 2 sensitive. And the insight of this paper was that you can think about this in terms of math. If I change the input, how does the output change? You can also think about this in terms of how many times did I use x, right? So I used x twice, so it's a 2 sensitive function. And so you get typing judgments that look like this. The context tells you with this 2 right here that you used x 2 times. And you can get this pretty easily with a couple of simple typing rules. This one says if you use x, then you've used it 1 time. This one says if I add 2 expressions, then I add together their context. So I'm just summing up the number of times I use each variable in E1 and E2. Okay? And this works really well. You can do functions in this kind of strategy too. You can say, hey, here this is a 2 sensitive function from real numbers to real numbers. And when you do application, so here's a 2 sensitive function, here's a 2 sensitive expression. When I do this application, what I'm going to end up with is saying I used y 4 times, right? If you actually did the application, you would get y plus y plus y plus y. So in the application typing rule, you get this scaling. If I have an S-sensitive function, then I have to scale the sensitivities of the argument by S. You can do the same thing for privacy, right? So we would like to track not just sensitivity, but also privacy cost using a linear type system. And this is what fuzz does also, but only for epsilon differential privacy. This is a Duet program, Okay, so this is new to our system. In our system, a context can encode privacy costs for variables in terms of epsilon and delta. So this is epsilon delta differential privacy. So the question is, what happens when I try to do this same thing? I apply a function. This is now a privacy function that's written in our privacy language. I apply it to something that is too sensitive. What I would like to do is to say, I'm going to scale the privacy costs in the same way that I scaled the sensitivities, right? And this is not okay to do, right? In fuzz, this kind of scaling was okay because in epsilon differential privacy, there's a special theorem that says there's a thing called group privacy, and it allows you to scale privacy costs. In other variants of differential privacy, you're not allowed to do this, right? So there's a fundamental difference between that first variant of differential privacy, epsilon differential privacy, and all the other variants, which means that the approach taken in fuzz doesn't work here. So the solution in Duet is to have two languages and to say there's no scaling allowed in the privacy language. So the sensitivity language is a lot like fuzz, right? Scaling's fine, everything works out great. But in Duet's privacy language, everything has to have a sensitivity of 1, and that's expressed here in the typing rule. Okay? And that's the big change that we made, is we introduced this separation between things that you write that are related to sensitivities and things that you write that are related to privacies. And when you're writing things in the privacy language, everything has to have sensitivity of 1. Okay? Okay, so I want to show, let's see, I'm going to have to, oh, there we go. My laptop's doing weird things on me. So I want to show, if you go to this website, we have an implementation of the type checker and an interpreter for this language. And there's also a browser-based version of it that I'm going to show you here. And my laptop's doing funny things, so wish me luck on this. And we have a bunch of examples from the paper in this drop-down box here. And you can see what they look like in the actual syntax that our language uses. And you can hit this run button, and it will tell you the type. And this right here is the statically determined privacy cost for this program. Okay? So I want to show one other example here, which is this one. So this is an example of a program that mixes privacy variants. So this chunk inside of here, we're in what we call a ZCDP block, meaning everything in here satisfies zero concentrated differential privacy. And then the program as a whole, we want to satisfy epsilon delta differential privacy. And what the Duet type checker will do is actually convert from one privacy variant to the other. And so the privacy cost that you see here in the type is a privacy cost in terms of epsilon and delta. The other thing that I want to mention, and there's a lot more about this in the paper, is the types have all these crazy M's and stuff in them. This is a type of a matrix, right? So this is that expressive matrix type that I talked about. It knows not just its dimensions. So this is an M by N matrix. It also knows things about the L1 or L2 norm of each one of its rows, which is useful when you're doing things like computing gradients. That helps you bound the sensitivity of gradient computations. And it also knows things about whether you are trying to track its L1 or L2 sensitivity, which allows you to more tightly bound the amount of noise that you have to add when you are adding noise to something like a gradient. Okay? And these were things that were well known in the differential privacy literature, that you need property x, y, and z from a matrix in order to do a good job adding noise to the gradient that you compute while you're training your model. But the matrix types that we had in traditional programming languages didn't support tracking those properties directly in the types. So I encourage you to take a look at this. Download our implementation if you want to look at it directly. If you find bugs, please let me know. I'm sure there's still bugs in there, but we're actively trying to develop this thing as something that people can use to verify practical algorithms. We have a bunch of examples in the paper, a bunch of case studies that have taken differentially private algorithms from the literature, and we verified those, and we're working on adding more. And I want to kind of reiterate that I think the message here is, if you want to satisfy something like differential privacy, verification is both a really important idea, because if you get it wrong, then your programs are silently violating your privacy, and because we've shown with type systems like Duets that you can do this actually in a really automated way. It's actually really easy for a programmer to hit that run button and get a proof that their program satisfies differential privacy. So that's all. Thank you.
Hi, thanks. You said that one of your goals is to enable people to be able to reason more effectively about differential privacy. I'm wondering whether you've had anybody other than the designers of the system use it, and if so, what was their experience like?
So we have not yet had anybody besides the designers program directly in the language, or people associated with working on it. So we've definitely had students program in the language, but they were also working with us and working on aspects of the language as well. So I don't think it's really fair to call them kind of outside users. You saw some of the code that I showed you. It is, I like to claim it's a practical language in the sense that there's nothing really crazy about it, but to a Python programmer, it looks pretty crazy. And most differential privacy developers are Python programmers. So that's kind of still a barrier. What we're working on is a version of this that can operate directly on Python programs, and that'll help a lot. We did have one experience working with a group that develops differentially private algorithms. We helped them write the Duet program, and that was very valuable to them because we actually found a bug in their algorithm by developing the Duet version of it. So that's the closest we've come so far, but that's kind of the goal.